Hello and welcome. In today's video lecture we will see the applications of various flip-flops. Part 2. In the last part we have seen the applications of flip-flop like debouncing switch, register, memory latch. In this part we will see shift counter and ripple counter. In the shift counter, it is like a shift register in which the output of the last shift register is given to the input of the first shift register, and the clocks are continuously provided. The data goes on shifting continuously like a ring. There are two types of ring counters, shift counters. One is the ring counter and other is the twisted ring counter. We will see step by step. So this is the diagram of ring counter using a 4-bit shift register. So output Q of the last shift register, last flip-flop is given back to the input of the first flip-flops. The clocks are given common to all the flip-flops and a common reset is given. Initially one of the flip-flop is set to make it high, the Q becomes high, and then the clock is given to all the flip-flops. So every time a clock is given, this is the pin diagram, this is the data of the QA. So once the clock is provided, then the data shifts here. So the QB becomes 1 and remaining are 0. Next time the QC becomes 1, remaining are 0. Next time the QD becomes 1, remaining are 0. This 1 is fed back to the QA. So next time the QA becomes 1, Q2, QB, QC, QD. In this way continuously the inserted bit is shifted towards right. So in all it has got mod of 4. In the ring counter, this QD is given to DA. So number of flip-flops in the register is equal to the mod of the ring counter. Next is the twisted ring counter. It is similar to the previous circuit except that the D is given the output from Q bar instead of Q. So here 0 would be given back. So in this circuit there is no any need of resetting. When you reset, all are becoming zeros, and then as Q becomes 0, the Q bar becomes 1. This 1 is fed to the D of the input, and then the clocks are provided. So this 1 goes to D, so 1 comes out to QA. Next time again the Q bar is connected, so Q bar is still 1 as Q is 0. As Q is 0, Q bar is 1, so 1 is given to the D, so that comes out to the Q. So for the 4 times the 1s are provided. Now after 4 clock pulses, as Q becomes 1 here, the Q bar becomes 0. Now 0 is fed back to D. Now 0 goes inside every time the clock is given because the Q are getting 1 now. After 4 cycles, again this Q becomes 0, so Q bar becomes 1 and it is fed back to the input. Hence again the sequence of 1s starts. So we will have this sequence like 1 0 0 0, 1 1 0 0, 1 1 1 0, 1 1 1 1, and then 0 1 1 1, 0 0 1 1, 0 0 0 1, then 0 0 0 0, and that goes on repeating. So this is the diagram shown. The next application of the flip-flop is the ripple counter. Ripple counter uses the use of T flip-flop. This is the JK flip-flop and its truth table. It has two interesting cases. states that when j is 0, k is 0, there is no change, and when j is 1, k is 1, it's toggle. So this j and k are short circuited to make the common t input. When j is same as k, there are only two states left. J is 0, k is 0, no change. J is 1, k is 1, toggle. So this is the truth table or transition table for the T flip-flop. Using the T flip-flops or JK flip-flops where the J and K are short circuited and made high, that time this state 1 toggle state. So every time the input clock is given, the output toggles. So it divides the frequency by 2. So dividing the frequency by 2, we get the mod 2 counter. Such mod 2 counters are cascaded in series, and we can have mod n counters. So this is the example of 3-bit ripple counter. There are 3 flip-flops, so that gives 3 bits, Q2, Q1 and Q0. Now each flip-flop has 2 states, so 2 into 2 into 2, that has 8 states. This is the transition table, and this is the timing diagram. You can see here the Q0 changes every time a clock is given. So first is change from 0 to 1, then 1 to 0, 0 to 1, 1 to 0, 0 to 1, 1 to 0, 0 to 1. It goes on changing, and then it again repeats back to 0. Now this Q0 is fed to the clock of the next stage. So this clock, when the clock changes from 0 to 1, as it is a positive age trigger flip-flop, that time the Q1 changes. So we can see change here 0 0, then 0. It will take 2 stages, 0 1 0 1. So it would be changing after 2 clock stages, and this is how we get the transition. Now Q0 is changing continuously after each clock pulse. Q1 changes after 2 pulses, and the MSB Q2 changes after 4 pulses, and it generates a number sequence like 0 1 2 3 4 5 6 7 and repeat. So it is a mod 8 ripple counter using 3 bits. Now using this 3-bit ripple counter, we can create any other mod between 1 to 8. So this is the example of mod 6 ripple counter. There are 3 bits as previous, and a trick is done so that as soon as the number 6 comes after 0, so 0 1 2 3 4 5, no problem. As soon as 6 comes, this is fed to a NAND gate. So 6 means 1 1 and 0. So these 1 1 inputs are given to the NAND gate. So whenever they both are 1, that time the NAND gate becomes 0, and this output is given to the clear pin of all the flip-flops. So they all become 0 0. Now once they become 0 0, this is the state that comes, and then it again continues to increment 1 2 3 4 5, again 0. So this is a continuous ring. So we have 6 states from 0 to 1, 2 3 4 5 and 0. So this is the example of mod 6 ring counter. In this way we can have any mod. We can have mod 5 counter if I connect it to 1 0 1. So I have to connect Q2 and Q0 to make a mod 5 counter. In this way any mod can be obtained. So in this video lecture we have seen 2 applications of flip-flops, that is the shift counters and the ripple counters. Based on this, here is the summary. We have seen the ring counter, ring counter, ripple counter, and we have also done the design of mod n counter. Questions. Based on this, you have to give the answers of the questions. Draw the logic diagram of mod 6 ring counter, then design mod 5 ripple counter and draw its timing diagram. How many flip-flops are needed to design mod 30 ripple counter? A mod 5 ripple counter is cascaded with mod 4 ripple counter. What will be the mod of the new ripple counter? You have to answer these questions. Thank you.